All right. Hi, everybody. So this is the next of the Physics 216 video lectures. Today, what I want to do is I want to start by just doing an example that will allow us to apply some of the concepts that we've been trying to develop recently, specifically concepts about gravitational orbits. The problem we'll look at is if we had a satellite in a circular orbit near the Earth's surface, how could we modify that orbit so that it becomes elliptical with a large eccentricity? Um, the other thing we'll do in this video is we'll start what will be the last major topic in Physics 216, and that will be the behaviors of systems of particles. So what happens if we have a collection of particles rather than just treating single objects as point-like particles? Okay, but so let's start with this example. And what we'll have to do is just remind ourselves of some of the things that we have been developing. So this is the radius of an elliptical orbit as a function of angle theta. Epsilon is the eccentricity of the orbit, and alpha was a collection of constants where m is the mass of the orbiting object, L squared is the angular momentum of that object divided by its mass, and k is gravitational constant times the product of masses, where big M is the mass of the object that is being orbited. Okay, so the example is the following. So we suppose a satellite is in a circular orbit near Earth's surface. The first question is a pretty easy one, and it is just to calculate the speed of the satellite. Okay, so here's Earth, and let's put our satellite in an orbit that is near the Earth's surface, and we'll call the radius of that orbit r0, and here's our satellite of mass m, and the Earth has mass me. If our satellite's undergoing circular motion, then its acceleration must be equal to a centripetal acceleration, and centripetal acceleration is v squared over r, where r0 is the radius of our orbit, and I'm using vc. The subscript just means circular. Okay, because we'll end up modifying this orbit to be elliptical in the future. So vc, just remember, is the speed of the circular orbit. Speed of circular orbit. Okay, but the force is just the gravitational force, and so it's g times the product of the masses. Let me put an e subscript for the mass of the Earth, and then the force goes as 1 over r squared. Now there's some cancellation. We can cancel the mass of the satellite, and that's kind of interesting because it tells us that it doesn't matter if it's a very large satellite or a very small one. The speed we calculate is going to be independent of the satellite's mass. There's also a 1 factor of r0 in the denominator that we can cancel. And if we solve the that just leaves vc squared. So if we take the square root of what's left, we get g times the Earth's mass divided by r0 and square roots. And so that's the speed of our satellite when it's in circular orbit. Okay, B. So when the satellite is opposite the moon, it is given a boost of speed. So maybe there's some little rockets attached to our satellite, and at some point those rockets fire and it increases the speed. So the question is the following. This boost changes the orbit of the satellite to an elliptical orbit. And what we're going to try to do is we're going to try to calculate what that boost needs to be so that when the satellite is furthest from the Earth, it is the Earth-Moon distance away from Earth's center. So calculate the boost required such that when the satellite is furthest from the Earth, its distance to Earth's center is the Earth-Moon distance. And the Earth-Moon distance is approximately 60 times the radius of the Earth. Okay, and so let's see if we could draw a picture of what that might look like. So we'll start over here with Earth. And so this is the radius of the Earth. Okay. And then we start with a near-Earth circular orbit. And this is a radius r0. What we'll end up doing is we'll assume that r0 is basically equal to the radius of the Earth. Okay, and initially, here's our satellite of mass m, and it is initially moving with the speed that we calculated for the circular orbit, but then we give it a boost. Okay, and it ends up that we increase its speed to some amount, and let's suppose that that speed that we boost it to is v0. So we go from the circular orbit speed to a speed v0, and after we do that, the orbit that we get becomes elliptical, and it looks something like this. Okay, this may not be a perfect ellipse, but you get the idea. And when it's furthest from the Earth, our satellite will end up over here, and this distance will be r1, which is going to be equal to 60 times the Earth's radius. And so that's equivalent to the distance between the moon and the Earth. Okay, so how are we going to approach this problem? So the first thing we might think about is angular momentum conservation. So angular momentum is conserved after the boost. Okay, so after the boost, there's no external forces. besides the gravitational force, which exerts no torque, so angular momentum is conserved. And so the magnitude of the angular momentum is the magnitude of m r0 cross v0. And so if r0 is here and v0 is here, those two vectors are perpendicular. So the sine of the angle between them is 90 to sine of 90, which is 1. And so what we have is m r0 v0 for our angular momentum. So that means the angular momentum per unit mass, this little l, is just equal to r0 v0, and that's equal to a constant. Okay, so for the elliptical orbit that we expect after the boost, r is equal to alpha 1 plus epsilon cos theta. And alpha is equal to ml squared over k. And k is equal to g times the product of masses. So when theta equals 0, and remember we chose theta equal to 0 to correspond to the minimum distance between the orbiting object and the object that's being orbited. So when theta is equal to theta 0, r is equal to r0 such that r0 is equal to alpha 1 plus epsilon, because cos of 0 is 1. So that means, let's see, epsilon plus 1 must be alpha over r0, and alpha is ml squared over k, and then we have an r0. But L squared, we already calculated, was just R0 times V0. So it's R0 V0, and then we have to square it, KR0. And so one of our results, therefore, is epsilon plus 1 is equal to m V0 squared. Then we have R0 squared divided by R0, which is just R0 divided by K. Okay, but we did part A of this problem, and so let's recall that in A, we found the speed of a circular orbit. In fact, I'll write down the square of that speed was just g times the mass of the Earth divided by r0, which we could write as k over the mass of the satellite times r0. Okay. That means r0 is equal to k over m vc squared, the speed of the circular orbit. And what we'll do is we'll take this r0 expression and we'll put it in right there and end up with epsilon plus 1 is equal to mv0 squared over k, and then r0 is k over mvc squared. And we get a pretty nice result here. That relates the eccentricity just to the ratio of the speeds before and after the boost. So this is the eccentricity of the elliptical orbit in terms of the satellite's speed before and after the boost. So VC was the speed before the boost, and V0 was the speed after the boost. And it's maybe not surprising that the bigger the final speed after the boost, V0, the higher the eccentricity of the elliptical orbit. Okay, so let's draw ourselves an elliptical orbit, and let's just remind ourselves of a few of the parameters of the ellipse. If we cut the ellipse in half vertically, which I didn't do a very good job of, so let me try again. Where's center? Somewhere around here, maybe. Then this is the semi-major axis A. And so the total width of this thing is 2A. And if this is one of the focal points, then here is, say, R0, and here is R1, and this distance is the eccentricity times A. So some of the things that we should recall then is that, let's see, if I was to take epsilon A and add it to R0, that would be this distance, which is just equal to A. Okay, but another thing that we can see is that if we take R0 and add that to R1, that's just equal to 2A. In fact, this was one of the defining equations of an ellipse. And so therefore, A is equal to R0 plus R1 over 2. Okay, so what I want to do is I want to start with this first equation, and let's just do a simple manipulation. Let's just isolate for epsilon. So we subtract off an A, then we'd get, no, maybe let's divide by A, so that we would get R0 over A with a minus sign if we move it over to the other side, and then a plus 1. Okay, and then we'll take this expression for A and we'll sub it in right there. So epsilon is equal to 1 minus R0, and then 1 over A is 2 over R0 plus R1, which is just equal to 1 minus 2 R0 plus R1. Okay, what I want to calculate is epsilon plus 1. The reason I want to calculate epsilon plus 1 is because then we could relate it to the speeds before and after the boost. Okay, so epsilon plus 1 is just going to be equal to 2 minus 2R0 over R0 plus R1, which is just equal to 2R0 plus R1 minus 2R0 over R0 plus R1, where we put our expressions over a common denominator. And then we have 2R0 minus 2R0, which cancels. And so therefore, epsilon plus 1 is equal to 2R1 over R0 plus R1. So finally, recall that first expression, epsilon plus 1, was equal to, it was V0 over V circular squared. So it must be the case, therefore, that these two expressions for epsilon plus 1 have to be equal to each other. And so v0 over vc must be equal to the square root of 2r1 over r0 plus r1. So this is one of the key results here. If we wanted a specific value of r1, where let's say r1 was supposed to be equal to 60 times the Earth's radius, and r0 was 1 times the Earth's radius for a near-Earth orbit, then we could just put in some numbers. And so we say if r0 is equal to the radius of the Earth and r1 was equal to 60 times the Earth's radius, then we would say v0 over vc would be equal to the square root of 2 times r1, which would be 120 times the Earth's radius, and then r0 plus r1 would be 61 times the Earth's radius. And so that's about square root of 2. And square root of 2 is 1.41. If you put in the 61 instead of 60, you get 1.40. So therefore, we need a 40% boost in speed. Okay, last question is, what are the speeds of the satellite at the nearest and furthest distances? Okay, so we already calculated the nearest distance speed. So I'll just make a note that sometimes perigee is called the position of closest approach. And so we found that what we had to do is we had to boost the speed by 40% of the circular orbit speed, but we calculated the circular orbit speed as gravitational constant times the mass of the Earth times the circular radius of that orbit, which we're just going to say is going to be close to the Earth's radius. And if you put in those numbers, you'll get 11 kilometers per second. Okay, at the furthest distance, which is called apogee, we can use our conservation of angular momentum. So we would require that L, which is equal to L over M, is equal to a constant. So at the closest distance, little l is equal to r0 v0, and at the furthest distance, it's equal to r1 v1, and so therefore v1 is equal to r0 over r1 times v0, which is going to be the Earth's radius divided by 60 times the Earth's radius times v0, such that v1 is equal to v0 over 60. And so you take your 11 kilometers per second, divide by 60, and it comes out to be about 0.18 kilometers per second. That result makes some sense because as our satellite moves further and further away from the Earth as it goes to its position of furthest distance, it's increasing its gravitational potential energy. If it's increasing its potential energy, then it must be losing kinetic energy, and so it's slowed down significantly compared to when it was near the Earth's surface. Okay, good. So that's that example of changing the orbit of a satellite using a boost in speed. What you could do is, and I don't know, this might be one of the problems in the homework assignments that I'll post to the website. You could imagine starting in a near-Earth circular orbit, and you give your satellite a boost like we just did, and that sends it into an elliptical orbit with a large eccentricity. And then you could imagine once it gets to its furthest distance, could you give it another boost so that you change back into a circular orbit, but this time the radius of the circular orbit is much larger than the original. Okay, so you can boost in and out of elliptical orbits and in and out of circular orbits. Okay, good. So that's the example. So now let's start the last topic of 216. And it's going to be systems of particles. All right, so let's start just by considering a system of particles. So it's just a collection of point particles. So consider a system of n particles with masses m1, m2, and so on up to mn. So we could draw a coordinate system, x, y, and we could say that, all right, there's a position vector, ri, that goes out to a particle with mass mi. And then there's another position vector, rj, that goes out to a particle of mass mj. And so that's just some of the particles, and then there's all these other point particles that exist in our system. Okay, so I'm going to define a notation here where I'm going to say Fij denotes the force on particle I due to particle j. And then we're also going to allow for the possibility that there are some external forces on our particles. So this is a force on I due to an external force. So not due to anything within the system. It has to be from something outside. Okay, and so let's consider particle I. And we could say maybe there is some external force, F external I, on that particle. And then maybe there's an interaction with particle J. And so this could be the force on I due to J. If these are massive objects, then there's a gravitational attraction, but maybe they're charged particles, and so the electric force is so much, it overwhelms the gravitational force by such a large amount that maybe this is just an electrical force between charged particles or something like that. Okay, so I want to write down an expression for the net force on the entire system. So F net is, okay, so this is net force on the system. So what do we have to do? the easy one is just to add up all the external forces. So we just look at every particle one by one, I equals 1 to n, and just add up the external force on each particle. And then what we do is we say, okay, for particle I, I'm going to sum over all particles except itself, and I'm going to add up all of these internal forces, all of the forces on I due to particles within our system. Okay, so this is the force on I due to all particles that are in our system. And then what I have to do is I have to do that for every single particle that's in our system. Okay, so we have this double sum, and just to get an understanding of its meaning, let's just write out some of the terms of this sum over I, and then a sum of j not equal to I, Fij. And let's do this for n equals 3. I'm just going to choose a small number so that we can easily see what the result looks like. I think we'll be able to, once we've done this, generalize to any number of particles, like Avogadro's number of particles or something like that. Okay, so this sum over I is going to be from 1 to 3. And this sum over j not equal to I is also going to go to 3. We're just going to exclude j equals to I. Okay, so first we just have I equals 1. So that means we're going to have F1, and j can't equal 1, so we don't have a 1, term, right? There's no force on particle 1 due to itself. So the first one we get is 2. And then we still have I equals 1, and then we go to j equals 3. And then that's where we stop, because we said n equals 3, so we can't go any higher than that. So these are the I equals 1 terms. And then we go, okay, I equals 2. And we restart the j sum from j equals 1. And then we have still I equals 2, but we can't have j equals 2, so we jump to j equals 3. These are the I equals 2 terms. And then finally, we have I equals 3, j equals 1, plus I equals 3, j equals 2, and then we can't have j equals 3 in this case. Okay, so these are the sums of all the internal forces. So this is the sum of all internal forces in a system of n equals 3 particles. All right, fine. But if we just think about this for a second, I think we'll realize that there's quite a simplification that we can make. We have to recall that Newton had his action-reaction law. This is the third law, which says that if there's a force on 1 due to 2, then there's a force on 2 due to 1 that has the exact same magnitude but is in opposite direction. And we could likewise say if there's a force on 1 due to 3, there's a force on 3 due to 1 that's exactly equal but opposite. And then finally we have the 2, 3 and the 3-2 pair. So then we go back to the sum of internal forces, we end up with a F12 plus an F21, but F21 is minus F12. And we have a F13 plus an F31, but F31 is minus F13. And then, of course, we could cancel the 2-3 with the 3-2. And lo and behold, this complicated sum just exactly vanishes. So therefore, the internal forces completely cancel, such that we have this sum over I and sum of j not equal to I, Fij is exactly equal to 0. Okay, so if we go back to our original expression, then the net force on our system is just entirely due to only the external forces. That's an amazing simplification, because you could imagine if you have Avogadro's number of particles interacting with each other, the internal forces could be incredibly complicated, but no matter how complicated they are, it must be that they all sum up to be 0. So what we're left with is that the net force is just equal to the sum of all of the external forces, and the time derivative of momentum is equal to the net force, and so we could write that the system momentum, its time derivative, is equal to that net force. And the system momentum is just equal to the momentum of all the individual particles added up as vectors. What we'd like to do next is we'd like to be able to write the momentum as the system mass times a single velocity. So we would like to define a single velocity that somehow characterizes the behavior of the system. So I'm going to call it VCM, and we'll see what CM means in a minute. So we're going to define this single velocity such that we can write that the momentum of the system, which we know has to be the sum of all the individual momenta of our particles, is equal to m, the total system mass, times this single velocity. So this is the system mass, where big M is just equal to the sum of all the masses of our individual particles. So evidently, to do this, we require the following. If we just take this expression and divide by the total mass of the system, then we isolate for this VCM, and so it must be that VCM is equal to 1 over the total system mass times the sum of the individual momenta, which could equivalently be written as the sum of the individual momenta divided by the sum of the individual masses. The notation CM stands for center of mass. So VCM is called the center of mass velocity. Okay, we could write this in another way. We could say, well, the individual velocities VI of our particles is just equal to the time derivatives of the individual position vectors. So there are Ri dots. But I could also pull the time derivative outside of this sum such that we could write this as d by dt of the sum of mi Ri divided by the sum of mi. Okay, but these two expressions have pretty similar form. One is a sum of m times velocity divided by the sum of m, and the other is a sum of m times a position vector divided by m. This thing in brackets is the center of mass position. Okay, so what else could we do? What if we just took a time derivative of the center of mass velocity? So let's take the center of mass velocity and take a time derivative of that. Well, that's d by dt of mi Ri dot, so Ri dot is the velocity. What we did last time is we pulled the derivative outside the sum. This time we can put the derivative inside the sum. And so this would be the sum of I, mi, and then d by dt of Ri dot. And then we divide by the sum of mi. But the derivative of Ri dot is just Ri double dot. And so the derivative of the center of mass velocity will identify as a center of mass acceleration, such that the center of mass acceleration is the sum of I, mi, Ri double dot divided by the sum of masses. So there's a center of mass acceleration. Here's our definition of center of mass position. And here's the center of mass velocity. So summarizing all of these results, therefore, we have our center of mass is mi Ri divided by mi. V center of mass is mi Ri dot divided by the sum of mi. And A center of mass is equal to mi Ri double dot divided by mi. Okay, so I'd like to see if we could, well, okay, let's just center of mass position velocity and acceleration. So I'd like to see if we could just try to spend a moment here figuring out why it was useful to define these center of mass quantities. Okay, So for our system of n particles, we said F external was just equal to the sum, F net, the net force on our system of particles, was equal to the sum of the external forces on each of the particles, and then all the internal forces canceled. And that was equal to m times, well, it was the time derivative of the system momentum, but the system momentum was the total mass of the system times the center of mass velocity. And so when we take the derivative, we get the total mass times the derivative of the center of mass velocity, which is just the total mass of our system times the acceleration of the center of mass. And so now what we can do is we could imagine a scenario where if the net external force on our system is 0, so that the sum of external forces on all the individual particles vanishes. It doesn't mean that there are no external forces. It just means that when we consider all of them, they add up to 0. Then we could say that V center of mass is equal to a constant such that the momentum of our system is equal to m times V center of mass is conserved. The reason we could say the center of mass velocity must be a constant is because if we set F net equal to 0, then that means the time derivative of the center of mass velocity is 0, which means that V center of mass is equal to a constant, so that when we take its time derivative, it vanishes. And we also know that that would result in the center of mass acceleration being equal to 0. Another thing we could notice about this expression here, and so let's get rid of these things so that we have the general expression in front of us, is that when we look at the equation in terms of F net is equal to mass times the center of mass acceleration, that looks exactly like Newton's second law for a point mass. So let's also note the following notes, that the expression F net is equal to the total system mass times the center of mass acceleration is just like Newton's second law for a point mass. In other words, it's as if all the external forces acting on the system are applied to a mass that's equal to the total system mass that's located at the center of mass position. So that's really a pretty extraordinary thing. You could have a system with as many particles as you like. There could be as many complicated internal interactions as you want, and all it boils down to is that you could just take all the external forces acting on that system, apply them to the position of the center of mass, and the system's center of mass acceleration will just be that total net force divided by the total mass of the system. So let's do an example. What we're going to talk about in the next, I'm guessing there might be 2 more videos for Physics 216, and what they'll focus on is rocket motion. So how does a rocket's velocity change as it's burning fuel, possibly in different types of environments, when there's drag forces, when there's not drag forces, when there's a gravitational force, and things like that. And so we're not going to do that complicated of a problem right now, but we can do a little rocket example. So a rocket has velocity, say, v naught, when it suddenly breaks into 3 pieces of equal mass. Okay, some of the information that we're given is that one fragment has velocity v1 is equal to v naught over 2. So that expression tells us 2 things. The first thing it tells us is that the speed of one of these fragments is half the speed of the initial complete rocket. The other thing it tells us is, because it's a vector equation, that this fragment 1 moves in exactly the same direction that the rocket was going initially. So this tells us that the first fragment moves in the same direction as V0 initially did. So as the rocket did before it broke apart. Okay, the other 2 fragments have speeds that are equal. So speeds, it said, so that's nothing to do with directions, but they move in directions that are perpendicular to one another. Perpendicular to one another. Okay, so that's all the information we're given, and the question is to find the speeds of these 2 fragments. Okay, so these 2 fragments that move perpendicular to one another. All right, so let's start by drawing a picture. So initially, what we've got is a complete rocket that has some mass m, and it's moving with some velocity v0. Okay, so then after the rocket breaks apart, we have one fragment that we're told moves with a final velocity at, let me change the length of the arrow to be about right. So it moves with half the velocity of the initial rocket and in the same direction, and all the fragments take away 1/3 of the mass. And then we don't know exactly what the other two fragments are doing, but let's suppose we have one of them and it's moving in this direction v1. It has mass that's 1/3 the initial mass. And so then we've got another fragment over here. It has to move perpendicularly to v1. And so we'll just put it in this direction. This is maybe v2, and it has a mass of 1/3 the initial mass. Okay, so if our rocket is in deep space, so it's not near any like massive black holes or whatever, there's no strong gravitational fields on our rocket, then we would say that the external force is 0, and therefore the momentum of our system is conserved. So that means the center of mass momentum, m times the center of mass velocity, is just equal to m v naught before the rocket breaks apart. And so it has to be equal to m v naught at all times if this momentum conservation is going to hold. Okay, so what's happening after? After the system momentum is m1 v1 plus m2 v2 plus m3 v3. But we know some information. We know all of the masses are equal to m over 3. And then we know that let's see, I've drawn this as v1 and v2 as the ones that are moving perpendicularly. And so we must have a v1 plus v2. And then the third piece is, let's call this v3, is moving with a velocity v0 over 2. Okay. So we just set the momentum before and after equal to each other. That's conservation of momentum. When we set them equal to each other, both have an expression of the total mass of the rocket, and so that's going to cancel. And what we must have, therefore, is v0 is equal to 1/3 v1 plus v2 plus v0 over 2, or 3v0 minus v0 over 2 must be equal to v1 plus v2. Let's see, 3v0 we could also write as, say, 6v0 over 2. And then when we minus v0 over 2, we'd get 5 over 2. And so therefore, it must be that 5v0 over 2 is equal to v1 plus v2. Okay. Now what we're going to do is we're going to do a little bit of a trick. So let's take the dot product of this expression with itself. So what does that look like? It's 5/2 v0 dotted with 5/2 v0 must be equal to v1 plus v2 dotted with v1 plus v2. Okay, so that's 25/4 v0 squared is equal to v1 dot v1 is v1 squared, v2 dot v2 is v2 squared, and then we get 2 times v1 dotted with v2. But we were told in the beginning that v1 was perpendicular to v2. Therefore, it must be that v1 dot v2 is equal to 0, right? The dot product involves the cosine of the angle between the vectors. If that angle is 90 degrees, cosine of 90 is 0. So this vanishes. We were also told that the speeds of these two fragments were equal. And so let's just call that v squared. And so what we end up with then is therefore 25/4 v0 squared is equal to v1 squared plus v2 squared, which is 2v squared. And so therefore v squared is equal to 25/8 v0 squared. Taking the square root, v is equal, so square root of 25 is 5. Square root of 8 is square root of 2 times the square root of 4, which is 2 root 2 v0. And so that is the speed of the two fragments of the rocket that move perpendicular to one another. Okay, good. So that's a good place to stop. Next time, what we'll do is we'll start thinking about the motion of objects that have variable mass. And so the example that we're going to think of when we're solving these types of problems is a rocket. So a rocket has variable mass because it's burning fuel. And as it burns fuel, it ejects an exhaust with a certain mass out of its back. And so we're going to use conservation of momentum with an object whose mass is changing continuously. Okay, so that's what we'll think about next time. Thanks very much, and we'll talk to you later.